In this lecture, we will see how to design 3-bit synchronous up counter, or we can say modulus 8 synchronous up counter. Now, what is the first step? Always we have to see how many number of flip-flops required. So, the moment we said the 3-bit synchronous, so small n is equal to 3. So, what is the maximum count? It will do 2 power n, so that is 2 cube. So, n is equal to 8. So, that's why we say modulus 8 synchronous up counter. So, these are the number of flip-flops required, right? So, that is the step 1. Next, what is the step 2? So, step 2 is we have to draw the state diagram. That is, what is the sequence it is following. So, we said it is up counter. So, 3-bit means, so from 000 to 111. So, first state is 000, then 001, then 010, then 011, then 100, then 101, 110, 111, and it should come back to 000 again. So this is the state diagram of this 3-bit synchronous up counter. So how many states? We will see 0, 1, 2, 3, 4, 5, 6, 7. So total is 8, but it will start from 0. So 0 to 2 power n minus 1. So total count is 0 to 7 means total 8 counts it will do. So that's why it is called mod 8 counter. So synchronous. So I am not using that synchronous again because we are designing the synchronous counter only. Next, choice of flip-flop and excitation table. So we have to choose which type of flip-flop we are going to use. So we can use either D flip-flop, JK flip-flop, T flip-flop. Here I am choosing T flip-flop. We can choose other flip-flops also, either JK flip-flop or D flip-flop. So but remember one thing, as the number of bits or number of flip-flops are increasing, it is better to avoid JK flip-flop. Reason is, when we are trying to minimize the expressions for 3 flip-flops, we will get 3 K-maps if I use T flip-flop or D flip-flop. If we use JK flip-flop, we will get 6 K-maps for this 3-bit synchronous counter. If we go for 4-bit the synchronous counter, we will get 8 K-maps when we use JK flip-flop. So that's why either go for T flip-flop or D flip-flop. But remember, in the exam they may give using any flip-flop. Okay. Now, so once we choose in this T flip-flop, so what is the excitation table of this T flip-flop? So it depends on the present state and the next state. So 00, 01, 10. So when I want this sequence, so what is the input I have to give for T flip-flop? So 0 to 0. Is there any change? No change. That means we should apply 0. So 0 to 1, there is a complement. So I have to give as input as T. 1 to 0, again it is complement. So I have to give 1. 1 to 1. So it is just following the previous state. So we have to apply the 0. So this is the excitation table of the T flip-flop. Similarly, if I choose D flip-flop, we have to draw excitation table for this D flip-flop. Next, what is the next step? Step 4 is we have to get the minimal expressions for this excitation. That is, we are using 3 flip-flops. So Q2, Q1, Q0, this is the present state, this is the next state, and these are the required excitation. So 3 flip-flops means we will get 3 inputs, that is T2, T1, T0. So this is the sequence from the state diagram. So 000 to next state is 001, then if it is a present state is 001, next state is 010, and so on. So after 111 we should get back to 000. Now, so when I want this sequence, what is the inputs we have to apply? So just see Q2 and Q2. So if I apply one first clock, so present state is 000, or the next state 001. So if I see Q2 is not changing at all. So 0 to 0. So from the excitation table we have to give 0. Then 0 to 0, Q2 only, again 0. Then 0 to 0, 0 only. 0 to 1, there is a what you call toggling, or we can say complement. So we have to apply 1. Next 1 to 1. So there is no change. So 0, 1 to 1, 0, 1 to 1, 0. The last one 1 to 0. So there is a toggling. So we have to apply 1. Similarly, see only Q1. So Q1 0 to 0. We have to apply 0 because it is following the previous state. 0 to 1 complement. So we have to apply 1. Similarly 1 to 1. So there is no complement. So means I have to apply 0. Next 1 to 0 complement. Apply 1. Next 0 to 0 no complement. So apply 0. Then 0 to 1 complement, apply 1. 1 to 1, so apply 0. 1 to 0, there is a complement. Next, if I see Q0, 0 to 1, 1 to 0, 0 to 1, 1 to 0, always Q0 will be complementing. So always we have to apply 1, 1, 1, 1, 1. I told you in the previous lecture, the T0, we can say the LSB always change its state. So the T0 input always we have to give 1. Now once we know this the truth table, generally we say, then we have to get the minimal expression for this T2, T1, T0. That is using K-maps. So I have drawn the K-maps already. So what we need to do, we have to just transform those inputs, or we can say outputs. So 000, see 000 to 111. So this is, I'm just mapping 000. So 0, 0, 0, then 1, next 000, next 1. So how to map? Simple, this one. So what is this? Q1, Q0. Similarly T1. So this is, see, 0, 1, 0, 1, 0, 1, 0, 1. So 0, 1, 0, 1, 0, 1, 0, 1. Now I can make a quad here, something like this. So what is this common? So in this, what is the common? The second one, which is Q0. Next, last one, we know it is all ones. So T0 is nothing but 1. Once we know these minimal expressions, the last step 5, is we have to draw the logic diagram. How many flip-flops? 3 flip-flops. 1, 2, 3. So we can use either negative edge trigger or positive edge trigger. So if I use negative edge triggering, and remember, all flip-flops will work simultaneously with the same clock. That's why it is a synchronous counter. So this is clock. So this is T0, Q0, T1, T2, Q1, Q2. This is Q0 bar, Q1 bar, Q2 bar. Now, what is the T0 input? Always it should be 1. Next, what is T1 we got? It is same as Q0. So just apply this one here. Next, what is T2? Q1 into Q0. So we have to use AND gate, and this output is come to T2, Q1 into Q0. So Q1 is coming here, and Q1. So this is Q0, this is Q1. So this is the input. So this is Q2, right? So this is MSB, and this is LSB. So Q2, Q1, Q0. This is the logic diagram. So we can verify the functionality also. I will check for 1 or 2 sequence. You can go for the other sequence also. Now, suppose initially all are zeros, 0, 0. Now if I apply the clock 1, so if I apply the clock 1, what happens, we'll see. So before we apply the clock, so first what is this? This is 0, this is 0. So what is the output? We'll get 0. Now the moment if we apply the clock, so the T0 is the 1, so it will toggle this output. So it is changed to 0 to 1, right? So the same moment this flip-flop also works. What is the input of this one? 0. So 0 means, will it change its state? No. So the output of this one is maintained the same. Similarly, what is the input of this T2? 0 only. The moment we are applying the clock, it will cease the input, that is 0. So will it change its state? No, same state. So 0, 0, 1. Now if I apply one more clock, so what will happen? So before that, see this, what is this input? See, 0, 1. So this is 1, this is 0. Output is also 0, right? Now if I apply the clock, what will happen? So Q0 always it's toggling mode. So it will change it to 0, right? But previously it was 1. So 1 means it also changes state. So it will change from 0 to 1. But this fellow will not change because the input is 0 again. So it will change to 0. There is no change actually. So 0, 1, 0. See, 0, 0, 0, then 0, 0, 1, then 0, 1, 0, and so on. So it will follow the sequence. Now we'll check at after, suppose all ones are there. Suppose all ones are this. Next, what will happen? When I apply the clock, what will happen? So before that, we'll have to check. So this is the 1. This is also 1. So 1 into 1, I will get now the 1. Now what will happen? So if I apply the clock, Q0 will change its state. So it will change it to 1 to 0. Then, so previously this is 1. So it is also changed its state. So 1 to 0. See the input T2. So it will also toggle the output. So 1 to 0. see all zeros. So again it will follow the same sequence, so 0 0 0, then 0 0 1 and so on, right? So this is the verification of this 3-bit up counter, which is synchronous, or we can say modulus 8 synchronous up counter, right? Same this mod 8 synchronous up counter can be designed using D flip-flop, can be designed using JK flip-flop also. You can try on your own. If you are getting any problem, please post a comment. In the next lecture we'll see this 3-bit down counter using D flip-flop. Okay.